Good afternoon, everyone. Welcome to the College of Engineering and Computing Sciences Industry Leader Lecture Series, where technology industry executives discuss a range of career and technology topics. The series is sponsored by the Region 1 of the Institute of Electrical and Electronic Engineers. Today's lecture topic is from top-level design specification to detailed design, and our featured speaker is Ed Palacio, president and co-founder of P&L Technical Management Solutions. At the bottom of your screen, you'll see a Q&A box where you can submit your questions throughout the event. Following the lecture, we'll take time to answer these live. I'll now pass it off to Dr. Babak Beheshti, Dean of the College of Engineering and Computing Sciences.
Thank you, Sarah. Hello, everyone. It is my pleasure to welcome all of you to the sixth and the last session of the Industry Talk Leaders Talk series this spring, hosted by the New York Institute of Technology's College of Engineering and Computing Sciences. My name is Babak Beheshti, Dean of the College. This series is co-hosted by our college as well as the IEEE Region 1. Our audience today is composed of IEEE professional as well as student members from across the Northeastern United States, in addition to the College of Engineering's current students and alumni and a number of distinguished guests. I would like to thank the College of Engineering's Dean's Executive Advisory Board, particularly its chair, Dr. Robert DeFazio, who has been instrumental in organizing this series. Please note that this lecture will be recorded and the recording link will be made available to you in a follow-up communication. Today's industry leader in the series is Mr. Ed Palacio, President and co-founder, P&L Technical Management Solutions Corp., and the IEEE Region 1 Director. The talk is titled From Top-Level Design Specifications to Detailed Design. Please review Ed's bio sketch available on the event website. Without any further ado, I will pass it to Ed for his talk. Ed?
Good afternoon, and thank you. Thank you, Dr. Beheshti. It's a pleasure to be here. I'm going to need to bring in my lecture. So can I share the screen?
Yep.
Thank you. Okay, so my talk today is from top-level design specification to detailed design. A little bit of my background. I came out of primarily military electronics in the world of electronic countermeasures. And so what we're going to do is we're going to see at least a view from what it takes. Okay, so we're going to be talking about understanding the requirements. Where do they come from? Detailing the requirements through the composition, allocating it through a functional identification, functional partitioning. Then we're going to say what goes into what, right? So we're going to allocate the functions. What does this look like, right? So we're going to have to go through physical partition and physical allocation. And then I'm going to take an oldie, very oldie, but goodie example of direct digital synthesizer replacement for a voltage control oscillator. And this is work I've done, I did 30 years ago. So it's a state of the art 30 years ago. But that's not really the key. The key here is the process of going down through the design choices. And it's about, how do you understand what you need to do and what choices you make in the process of designing? And then I'll have some final remarks. So the first is, where does it come from? Where are the specifications come from? Now, the specifications can come from many places. In my world, where the government would provide us very specific set of requirements, the requirement could be directly stated. In other words, the tuning speed shall be whatever milliseconds. Or the requirement could be reference. The reference could be, let's say, in compliance with IEEE standard, whatever. Or the requirement needs to be derived from a previously specified requirement like battery life or total size, weight, and power, or mean time between failure, which is a requirement at the top level, system level, which then needs to be broken down, allocated, and budgeted to the different aspects of your design choices. But it could also be driven by your choices. In other words, you're going to have, when you implement, and we'll talk about it, you may find yourself that you slant towards, let's say, high-speed processing, or you slant towards high-speed analog, or you slant towards software. And so you're going to start driving some of that requirement to the places that you feel comfortable with. And actually, quite important, it will be driven, but what is available with respect to technology and product maturity. In my world, it was not state of the art that we had to deal with. It was producible state of the art, right? And so if you're looking to build something that's going to be replicated and made in, multiple pieces, you really start to, if you're going to push the boundary, you really need to push the producible boundary, right? If not, it's interesting, but not implementable, right? In what you're trying to do. So it's going to have to be technology, but it's producible technology at some level of maturity. One of the things you have to do is you have to take all those requirements and you got to decompose them. Think of them as blowing up all the requirements. You're going to look at all the shall paragraphs. You're going to unbundle them. You're going to list them all individually. And in a smart design, you're going to reference them always back to the source. And we'll talk a little bit more about that as I get into the discussion. But let's take a very simple requirement. The room shall be 12 feet by 18 feet by 9 feet high with 2 windows, an outside wall. It will be well lit and suitable for all office work. So how many requirements do we have for something like this? Well, the room dimensions were directly defined, but you're going to have 2 windows. That's defined, but which wall, size of window type, where placed, not defined. Well lit, that's directly defined, but to what specification? Is it an OSHA? Is it office space? What fixtures, where placed, where switches? Suitable for office work? Well, flooring, painting, ceiling, finishing type, fire alarms, fire suppression, air conditioning, all sorts of things that go into this entity. Is there an industry standard? Is an OSHA standard? Is a local building code? And derived, where's the door? What size? What type? What lock? So you can see that if all you did was generate that requirement, you could get a large amount of implementations of that requirement, all of them compliant, but all of them highly different, right? So what it tells you, if you're going to define, you need to define it very well. Like a great systems engineering group, said, you got to tell me what you want, what you really, really want. Just tell me what you want, right? You got to tell them what you want. Now, where does the requirement decomposition ends, right? It ends when all the requirements are identified, numbered, and separately listed. Their source document and paragraph is appended. And eventually, where the requirement was allocated and budgeted in the functional and physical design. Now, this is critically important, right? Especially, and by the way, not just in my world, which was a highly documented military electronics type of world, but if you are designing anything, even in a commercial world, the reason you do this is you always want to come back and say, so why am I doing this? And if I change, what else changes? Because everything is tightly integrated, right? So you need to keep track of the requirement. You need to track how it was budgeted, and you need to track that if you make a change in one place, you need to go back and see what does it mean at the system level performance, and what does it mean going down to the lower level requirements, right? And hopefully you're going to do this in a tool or a document that is configuration controlled. And this is critically important, right? As we start flowing down the design into its component parts. So you're going to do a functional partition. Well, all systems have functional elements, right? That allows them to fulfill the requirements. In my world, let's take something like a sensor system, right? There will be a function of signal capture, signal identification, signal processing, signal reporting, controls, system management, reporting and displays, et cetera, right? So there's going to be a lot of functions, what the thing does in a functional way. So once all the logical functional elements are defined, right, you got to go from all individual specification requirements must be allocated to one or more functional elements. If you have a dangling requirement, you probably haven't identified all your functions. And why one or more functional elements? Okay, let's take a system level requirement. In my world, response time, right? We designed a lot of electronic countermeasure system, which means, you had a very critical design requirement from the time the missile's guidance signal got up to the time you had to respond to it, right? And why was it critical? Because if you didn't do it fast enough, you were probably dead, right? So it was critical. So that requirement, okay, so something as system response time affects affects the aperture design, the system sensitivity, signal processing algorithm and speed, the interleaving, the signal identification, the processor speed, the processor structure, display processing, response assessment, response process, et cetera, et cetera, et cetera. And if you have a requirement that says system must respond within 500 milliseconds of the signal going in the air, now you have to allocate every bit of that. Oh, excuse me, let me close my door. I have some background noise. Like I said, excuse me. But you're going to have to budget and keep track of every piece of time from the time you saw the signal to the time you generate the response, and it better be less than 500 milliseconds, right? So you have to allocate it all and make it happen. So now we get to a point, so we have, let's see, did I miss something? There we go. So now we're going to do physical. And by that, I mean the design implementation, right? And that will be driven by choices and constraints. So let's say it could be such thing as size, weight, and power, response time, throughput, reliability, maintainability. We'll provide constraints because you're going to have to live in your design in such a way that these specific requirements have to be met, given your implementation. The other thing that's going to impact that is the state of the producible art, right? What can be manufactured, replicated with a high degree of quality and confidence. And I'll give you a for instance. During the time that we were involved here, I had a large design team, and we were looking at the implementation of the microwave slices, the microwave design. And my design engineer comes back and says, boss, we have a great design and all, it would meet everything we want. However, the factory floor has to control 1 mil placement and 1 mil spacing. And so I bring my manufacturing group. And at that time, by the way, 1 mil may not be a big deal today, but 30 years ago, let me tell you, that was a big deal. And that was a big deal in placement. We had a 3 mil factory. So I have a wonderful design, but totally unimplementable in my factory, right? So it was interesting that everything could work in a 1 mil setting, but my factory was a 3 mil factory. I cannot implement that. And everybody knows, right? In the microwave world, it's all about physics, right? It's physical. It's the controlling of the copper, controlling of the wall, controlling of the gap, controlling of the placement, right? All those things are essential if you're going to maintain your microwave performance, right? So we couldn't do it. So we had to figure out a different way. The other aspect will be your design choices. And that is based on what the staff feels comfortable with. What are their preferences? What are their skills? What are their capabilities? If you are in a house that has great programmable logic design, chances are you're going to put a lot of stuff in the programmable logic. If you're an excellent analog house, you're going to be moving some of your circuitry into the analog world. If you are a high-speed processing house, you may put some of the implementation in software. So it really is going to be based on what you feel comfortable with, what are your preferences, which is why, let's say, a major system design that goes out to where I worked, or today L3, Northrop Grumman, Raytheon, and they will all be implemented in a slightly different way. They would all meet the overall systems requirement, but when you broke it and looked inside, they will be different allocations and different implementations of the various design requirements, all compliant, all with different pros and cons, but it'll be driven by the staff and the preferences and the capabilities. And we're going to discuss this when we get to the direct digital synthesizer example at the end. By the way, the implementation of the allocation, right, the design, the physical design, is probably the hardest part of that aspect of design, right? The process of allocating the function and thus the requirement to the physical entity. And the system architect, the person who's responsible for keeping track of everything, right? must understand the trade space and the capability within each element of the trade space. So if you need to know where what you can do in the microwave world, what you can do in the analog world, digital, the throughput, the timing, all the things associated as you make the choices of where you put your design and the implications on size, weight, power, time. I mean, all the things that you are concerned, right? Have an assessment depending on how you place it. And as I stated before, every choice has a pro and every choice will have some type of con. This aspect of design, therefore, becomes iterative as the various options are synthesized, model, and then validated for compliance. And for very good design practice, by the way, is to make sure that complete functions, reside in one physical entity. Now, let me tell you, that's easier said than done. And certainly in today's modular world where you're thinking to have common modules and then you integrate them together and you get a different type of system. Certainly a physical and functional partition or tight physical and functional partition is very important. But if you work in an unmanned air vehicle and size, weight, and power is everything, I tell you, what you find yourself doing is you end up using every square inch of that board because you don't want to add another board, right? And so maybe the physical and functioning is not that tightly coupled. In my world, we're going to send something to space and size, weight, and power is everything. You may find, half synthesized and close to a receiver, the other half somewhere else, right? But in a good design practice, a synthesizer is a synthesizer card, a receiver is a receiver card, a transmitter modulation is a modulation card. So that way, you can upgrade your system by just replacing cards without having to design everything. But like I said, in the end, everything has to go somewhere. Now, you notice that when we were starting the design, we came from the top and headed towards the bottom, right? But now that you're down at the bottom, you kind of got to come back up. If you were to look at it in classical system engineering, that's the V, right? The famous V, where you're coming down from top level design down to the lowest level, and then you model and test as you're going up and build up. So you cannot start the design until a bottoms up assessment is conducted to make sure that the specification indeed are going to be met. And so you're going to now take all your design, all your allocations, all your budgets, and you're going to put it in some type of model. And you're going to do math models and analytical models and detailed analysis of the expected performance at the lowest level. And then you're going to sum them up as the requirement is aggregated back up to the source at the system level or at the deliverable level. And as you go through your design and you make your design choices, and let me just say, it's iterative because some of your choices may not work, and then you may have to come back, and then you have to change, and you may have to reallocate of what is doable and not doable in the producible technical, state of the art. To do this, you need some type of model where you can make these assessments, right? And it has to be, validated as you move through the design. First at the CAD level, a computer-aided design level. Then as you get component and you measure component, you take that component actual data, you put them into your models. Brassboard data, you take them into your models. You take them from spec sheet, you take timelines, you take latency. But as you are building up and making your design and your design is progressing and maturing, you're taking data and cranking it back into your model to kind of tell you whether or not this is indeed going to be a compliant design. Now, I'm sure there are many tools, and I haven't designed anything in a very, very, very long time. So, Ed and tools are not, I'm certainly not conversant in today's tool. But at one point in my life, a tool like DORS was a critical tool, right? It would allow you to flow down your requirements, track the requirements, where they came from, where they were allocated, and you can have that capability going back and forth. And this is critical as things change. You make a change at the top level, you want to see everything allocated, that gets affected on the way down. You make a change at a bottom level, you want to see how everything gets impacted on the way up. So a tool, a system requirements flow down to is critical. And your tool, in turn, gets fed by all the various design tools that you're going to be using to design your specific area. So, CAD tools for everything: systems, analog, microwave, digital design, mechanical, stress, thermal, reliability, etc. Even the programmable logic can provide you, design tools can give you functional level performance and timing. Same thing as software tools. As you are cranking through your design and you're putting them through your CAD systems, you're feeding it back to the system architect who's looking and see how these specific performance aggregates up to the critical performance of the system. And you're going to identify key performance parameters. Now, key performance, there are thousands of parameters or specifications or requirements in a system, but there's probably a dozen that are truly, truly critical. And by that, I mean that regardless of how many others you met, if you didn't meet this one, the system didn't work. As a for instance, it doesn't matter that you make the size, weight, and power, and all the things associated, and reliability and maintainability, if your electronic countermeasure systems cannot respond within time of the missile hitting you, it's very interesting, but an irrelevant design, right? So there are going to be some very, critical stuff that doesn't matter what happens. I can talk about the other and maybe get a little forgiveness, but in this one cannot be in any way violated. So you got to know what those are. In space, it could be size, weight, and power because those things are critical. It could be many things, right? It could be system sensitivity, whatever it is that your customer is coming to you to resolve their problem. That's the key performance parameter. Know them, watch them, allocate them, budget them, and measure them as they progress from paper to implementation. And do all this under some type of project management discipline that allows you to kind of track your effort, plan, measure, control, report, correct, and modify. So let's go to direct digital synthesis, replacement for an oscillator. So I'm going to tell you where this happened. Well, it certainly happened before many of you were born. So let me just say, this is in 1991. And in 1991, high-speed digits were slowly coming. By that, I mean things in the nanoseconds. And going under a nanosecond was starting to just be implemented in the labs. And so we had a design that had to do two things that previously were done in separate systems, and that's communication and radar. So it had to provide the very fast tuning speed for communication. Communication is all dead on, narrow band, dead on, precise. Frequencies set on, very clean narrowband signals. And then it also had to do the opposite. It had to provide wideband performance required for going after system radars. And those two things normally had to be built a very different type of performance. And by the way, it also had to be better, higher level of reliability that could traditionally be achieved by analog and voltage control oscillator circuitry. It had to be smaller in weight and power, and it had to have significantly higher mean time between failures, right? In short, we had to provide the signal characteristic of a communication device as well as the modulation and wideband characteristic of an airborne jammer. Now, this is in 1991. So the team, we actually broke ourselves into two teams. We had an older team of older engineers that were going down a path of designing this with state-of-the-art VCOs, voltage control oscillators. At that time, hyper abrupt. And then we had a significantly younger team of engineers that were maybe 2 or 3 years out of school, and say myself and my partner were in our 30s. We were leading a team of very young, I guess because we really didn't know it was not doable, to come up with a digital solution. So the VCOs at that time, the producible way of doing this. However, if you ever dealt with analog circuitry, it was significant analog for the modulation, inherently tweaky, inherently low reliability in the analog designs. At that time, however, there was digital circuitry now being put in ASICs that had 2 gigahertz clock speed. I know this is not a big deal now, but I will tell you in 1991, that was a very, very, very big deal. Right? Now, if we could implement with that. We would get excellent tuning, speed, and accuracy. However, it's not proven in radar. It required the development of very fast 12-bit D-to-As, again, pushing the state of the producible art. It required high-speed 24-bit parallel buses. It required completely different packaging and cooling techniques. And yes, that was a design that had never been previously implemented. And for those of you who like to look at stuff, but if you don't know what a direct digital synthesizer, they're really a set of accumulators. They accumulate at different speeds, and the increment of the accumulator gets added every clock, and from there you can generate frequencies by actually changing the increment that you put into the accumulator. So we replicated VCO performance with a totally digital, very high speed adders. Running at very high speed at the time. But by doing that, now we can bring all the digital techniques. We could quickly modulate by switching inputs and provide an awful lot of capability in pretty compact digital cards. Now, so here we go. We came up with a really smart way of doing it. But as everybody knows, high-speed digits is super fast. Super fast digits are super hot, right? So along with the inherent high speed of the signals that had to be contained in a small space, we had to develop the way of cooling them. So we went into, at that time, again, big deal, ball grid arrays, and all sorts of the thermal design associated with our devices. So we had to look at metal matrix core. We used the ball grid array both for thermal and for signals. We ended up using diamond balls in some cases to pull the heat quickly. The modulation had to look like analog. And so we had to figure out how to make digital noise really look analog-like. And if you looked at noise, right, typical white noise has a very specific look. And digital noise, by definition, is being created digitally, right? So we had to figure out a way to do digital noise that would have all the characteristics what we were looking at for white analog noise. And of course, the requirement process now had to include all the requirement imposed by our choice of digital solution, right? So the allocations now had to be made under a logical partitioning that was digital based. The analog requirements now had to be translated, allocated, and budgeted in the appropriate physical component. And the digital solution drove the requirements for everything: the command structure, the clock speed, the digital bus speed, the chip placement, the ball grid array design, the thermal design, and the analysis and modeling had to be done with a new set of tools, right? To deal with the fact that we chose to go digitally. I think this is my last slide. So what do I say here, right? Look, the discipline design process is necessary, but it's not sufficient to guarantee success. Just because you're disciplined doesn't mean you're going to be successful. The critical aspect of this success is the designer understanding the phenomena you're dealing with. You need to understand the phenomena. You need to go a level above your small world of just digits and understand the phenomena you're creating. In our world, phenomena was microwave signals that have to get into a missile's processing system, the usage environment. For us, the weapon system and the tactics, the customer wants and the needs, and more important, the limitations of the technologies chosen, right? In short, knowing your limitations and your possibilities and your customers' problems and preferences and moving forward in a disciplined structure approach is the only way. It's the only way to succeed. And with that, I'm done with my talk. I can take questions.
Okay, thank you so much. It looks like we have just one question in our Q&A box. Feel free, anyone, to submit any questions. So we have a question from Bruce.
So here I see a question from Bruce. Requirements and specifications. Look, requirements are everything, including specifications and functionalities, right? The problem space, a requirement can become a spec, right? At some point, the specification is all addressed all in one place. Everything that you have a shall needs to be addressed. A requirement that it must be this big, and then as well as can turn into the detailed specification. And yes, I use them interchangeably, but at the end, everything that must be generated needs to be placed somewhere. And how did we capture our decisions, Bruce? The capturing of decisions in my world, the decision is captured as the implementation of the design is moving forward. We would hold very specific major reviews. For instance, the first configuration is the aspect configuration. The next set of configuration, which is generated in the document, is the as allocated. Then the first set of system level design and requirement is generated, and all that information is captured in a set of documentations. After that, as we start generating preliminary design, we would then capture that at that level. We will then go to the critical design, which everything is now in drawing, and then we will capture that level. And in all cases, the information always went back and had to be validated against this, through the modeling systems all the way through to the requirements. And so the next configuration becomes the as-built configuration. The next configuration becomes the as-tested configuration. The next configuration becomes the as-delivered configuration. And every time we made those, and by the way, every configuration had slightly different implementations, right? Because things change as you move through the process, and you captured it, and then you validated, and then you held it in a configuration, all the way to the as-delivered. Now, Ramon asks, any preferred method in software? To tell you the truth, I'm not a good person to answer that today. But I will tell you this. The design itself and the domain itself will define what you need, right? If you're doing visual, if you're going to do something that is going to be put on a computer screen, then you have one type of software that's best. If you're going to be using something that has to be real-time specific, it may be completely different. And by the way, your customer may decide what method of software you're going to use from a supportability point of view. From my viewpoint, the government would always say, the software has to be, because this is the competency of my team, right? And so for us to supporting it over a long period of time, this is the software you're going to use. How did you handle situations when it seemed, Ravi, this is a very good question. How did you handle situations when it seemed that the combination of customer performance requirements, size, cost, and power just seemed impossible? By the way, let me just say that I've had significant experience in this arena. So how do you do it, right? So first, you have to make sure that you are truly correct, that the requirements, the size, cost, and power, and your implementation, because be aware, your size, cost, and power is based on your implementation. And we stated there are many ways to implement. So have you gone down the path that all these different implementations doesn't get you there, right? Then the only place you can go is back to the customer. I have to tell you that I've had programs canceled because we could not implement. And I've gone through significant cancellation policies and then legal issues where at the end, the customer, after they canceled us and we fought it legally, they recompeted the program with a completely different set of achievable requirements. So they learned from it, but it did not really do very well with us. How does this level of requirement generate work with agile software? So I will tell you this, so I do get involved in agile, right? So agile process is focus on what's critical, implement it quickly, give your customer something they can assess, and go from there. And I think it has its place in generating software to some extent. But the government, you see, the other implications of agile is that not all the specifications are as equally important. And okay, so if you have a customer who buys into this, if you have a customer that needs something quickly and you're working in a software world and you want to quickly show it and get the customer feedback, which is what agile is so absolutely good at, right? That's great. But if you have somebody who wants to make 1,000 pieces that all look alike and perform exactly, it's a whole different discussion. I haven't figured that one out yet. What is more critical, budgetary design in a commercial setting? Oh my goodness, what a great question. But yes. So tell me, I'll give you an answer that may or may not answer your question, but in my world, being technically blue, and I'm going to explain that. Okay, so the government says, red, you don't meet the spec; yellow, you're marginal; green, you meet the spec totally; blue, you exceeded, right? To be blue and give the customer more than they want, if that doesn't come within 5 to 10% of the cost, nobody buys it, right? So you need to understand. You need to understand what the market will bear. And so budgetary constraints may be very critical. And design. Now, in the commercial world, you will constantly make a trade between what I'm giving and what it's costing. Be aware, in the commercial world, pricing has nothing to do with cost, right? Pricing is what you get. So if you can, that because Apple, the first set of Apple phones were being sold at $600, right? At that time, when Samsung showed up for $300, Apple magically brought their price down to $300, and they still made money, right? So it has nothing to do with costing. But if you are in the commercial world, your costs better be below your price, right? So those are trades that you test within your customer world, right? Ivan, how do you work with customers where the requirements are either less well-defined or seem to continually shift? You work very hard in that. And interesting, so we just talked about Agile. One of the things that Agile was trying to fix is exactly that, right? How do you get into but I'll give you, for instance, the part of my world that knew that we were defining something. And so you tie yourself very tightly to the customer systems engineering and requirements people. And you are working back and forth to show and force them to make decisions as you start becoming more and more defined as you're moving towards a final configuration. But let me go back to Agile. One of the reasons to Agile, if you ever get involved in very large software systems like ERP, enterprise resource, and you're buying this enormous thing with tons of software, and now the person delivers it, right? The company delivers, and you start using it, and you find that it doesn't have the functionality or have the display you want, and you say, it took forever for me to find out that this implementation is not what I want, right? So one of the reasons Agile is there is explicitly to deal with that problem, right? That I want a customer to give me feedback as I'm designing. So you have to very tightly couple your customer. Now, if your customer is not as defined as mine being, let's say, a US Air Force, if your customer is really the American public, now you got to figure out how are you going to validate your requirements and your choices, with the customer. And a lot of people use that by bringing in focus groups and doing whatever they do to get their feedback from an actual customer, what they're doing. But this is a tough thing. Bruce, that appears to be a capturing of a solution, selected alternative, not the set of alternatives in the support of the criteria requirements. Bruce, I to be a capturing of the solution. Yeah, at the end of the day, I capture, but to your point, a set of alternatives. At the very beginning of our requirement, again, in my world, where you start going down a path of analysis of alternatives, you start doing that. At the very early stages of system design, you proceed with multiple, various alternatives. At some point in time, you go from alternatives to a detailed design. So yes, the alternatives have to happen way up front. Because at some point in time, you're not designing a set of alternatives. You are designing a selected alternative once you make a decision to go down to physical partitioning. Ramon, I meant more on the system design perspective, like using V-shape to approach the project or using Excel to track your system requirements and the cascaded effect is upon changing some part of X. The system design perspective, which I believe I spoke, followed a V-shape. So we would use a V-shape approach to take you down. Whether you use an Excel or you use a system level tool that is a bit more sophisticated, that absolutely, to track your system requirements, and your cascade, and then you model it and take it all the way back up. I don't know if I answered your question, but I forgot the first part of your question. That was 7 questions ago. Vincent, where are you? I'm working on a research project where engineering students are working with medical students to create a medical device. Do you have any tips? Yes. Get very, very, very involved with the medical team and make sure that you do not throw things over the wall. In something like this, you need to be able to understand the domain application, which is what the medical students have. And you are bringing a technical aspect, but may not have the domain application. And to design something without domain knowledge is totally futile. So for me, the medical students have to be in every one of your discussions as you start, and you have to learn to speak their language as much as they need to learn to speak your language so that you can actually communicate. But in this case, being able to explain the implications of your design to their phenomena, and for them to explain the phenomena so that you can build a design, is absolutely critical. Mohammed, do we have good software that can handle requirement system and analytical models? You know, I would hope to say yes, but let me just say I haven't played in this world in a long time, but I cannot believe that today's world does not have those kinds of tools. I would say somebody smarter than I or more current than I can answer that question, but I have to believe so. Philip, how is your process different depending on goal and funding? Well, so let me just say, this is a very good point, right? If you are in a best efforts contract, let's say I've been involved where we're trying to do something that has never been done before, and the customer understands has never been done before. You tend to have a lot more discussion and a lot more ability to trade between the various specifications or the various requirements, right? But if you're moving down and the funding, again, it's all about the type of risk you take as an organization. So when I'm involved in a program that does not have a lot of detail, the funding tends to be more of a forgiving funding, cost plus, best efforts. You keep working until I run out of money, but I'm not really going to get sued. Now I'll flip that over to the type of contract that in many cases we find ourselves, which is, let's say, a fixed price. By the way, you guys, the world is always fixed price, right? You go and you buy a car, they give you a price, you buy the car, you don't, negotiate what's in it. I mean, you may have, but within a constraint, but you're not designing the car. But in a world where you have a high level of risk because now you're being held to a specification that must be met, right? You accepted a type of contract that has all sorts of implementation. That's a whole different world, right? And so, yes, research where you're trying to push something that you would never take a research project on a fixed price contract, right? Nobody will give you a production project on on the same kind of funding that you would do on research because it didn't make sense. So the discussion is the funding has to fit the risk being taken and the level of certainty that you're being asked to work in. Craig, in New York, we're redesigning the electric grid to be renewables intensive. Well, let me just say, no detailed design can happen without some type of process that I just stated, right? You have to define your endpoint. You have to define what you're going to read. Not every, people cannot just be free thinking all the way along. At some point in time, you have to architect the signal. At some point in time, you have to generate flow down requirements. At some point in time, you're going to define the final product so that everybody else can work together. So a process like this, whether it's as detailed as you find for the military, but a process like this, and I want to say a disciplined process that keep tracks of choices made and the implications in the specification or in the performance by those choices must be documented for you to get to an endpoint. Okay, Mohammed, how may we know the stakeholder requirements of feasible and solution exist? Let us say that if you accepted the job, you had to do a certain amount of work upfront of feasibility and solutions, right? You would never, unless you were in a research environment. And in a research environment, part of the research is saying, if you have a smart failure, but you have to be, if you're going to take on something, right? You would not take on something that you didn't think was feasible. You should not take on something that you don't think a solution exists, unless that's exactly what they're asking you to do. Do an investigation to see if there's any solution. Okay, well, that's feasible, but otherwise, being feasible and having a solution would be the only reason you would take that job. And yes, Brian, requirement verification. If I were to give you a view of requirements specification from a discipline approach, you validated every level, right? You validated the bottom level, and then you sum up, and then you validated the next level, and then you sum up and you validate until you validate as early as possible to make sure that your design is moving in the right directions, which means that if I have componentry, I'm going to check components, component level performance before I put it into a subassembly, and then I'm going to check subassembly level performance before I put it into a system, right? You're gonna verify from the bottom up, and then at the top level, you're going to verify, system level functions, given all the data that you build along the way. What you don't want to do is you don't want to wait for everything to be built and then only test it at the top level, because it'll take you forever. Bruce, the tool sets are being tracked by MBSC and other groups at INCOSE. I would be surprised if IEEE groups were also there. I think you're correct, Bruce. It would not surprise me if IEEE groups are in the middle of this. Keep on going up, which is one of a few that does requirements through allocation sum model. The current MBSC process has grown from the design that it has described, with the addition of capturing multiple discipline applying structure model. Good, thank you. Hey, I hope you guys enjoyed it. I hope you did. Thank you for all the questions. It's interesting, good set of questions. I did the best I could, given that I'm an old guy and now consult primarily in program management and business capture. But I enjoyed it, so I hope you enjoyed it as well. Thank you all for being here. Thank you, Babak, in the College of Engineering, and certainly the IEEE loves these things, so we are extremely happy that we are part of this. We have been allowed to be part of this series, so thank you all. Without much ado, I'll say goodbye.
Thank you
so much.
Thank you, Mr. Palacio, for the great talk and also great questions. Thanks for being a great audience. I think we'll have Bruce as our next speaker.
I love them. He was great. All right, be good.
Yeah. So thank you all for participating in the event. My thanks go to my colleagues who made this event happen. Dr. Rob DeFazio, Assistant Dean Jane Polizzi, Ms. Carmen Marmo Savinetti, and of course our own Ms. Sarah McGuff. Please stay tuned for our next talk series to commence in the fall with more great topics presented by great industry leaders. Have a great day.